Thank you. Hello, everyone. Today I'm presenting on PCB electrothermal and thermomechanical analysis workflow. Here are the topics I'd like to discuss today. We'll start with an introduction to PCB modeling requirements. So there's different information during the design process that we feed into the PCB model and different results we want to get out. So we're going to take a look at kind of a high-level description of what these design tasks are. Next, we'll look at PCB thermal modeling methods. So depending on where you are in the design process, there's different approaches that are commonly taken to represent the copper in the board and the effective conductivities of that PCB for temperature prediction. One of the approaches to modeling a PCB is the material map. That's an innovative approach we've taken with a couple of our products that I'd like to introduce you to. So we'll take a closer look at it in this section. The material map is the enabling technology for electrothermal co-simulation plus CFD and thermomechanical plus CFD in our products, and I'd like to illustrate both of those with a little bit more of a technical discussion and examples. So they're the last two topics we'll take a look at. The most common modeling requirement for PCBs for a thermal or mechanical engineer would be temperature prediction, the ability to power the components on the board with some thermal dissipation, be able to model the components and the printed circuit board, and predict the temperatures in an environment, whether it's forced convection, natural convection, conduction, cooled, or any combination of those. Another modeling requirement for printed circuit boards is the ability to include self-heating or the joule heating that takes place in a printed circuit board. Anytime you have current running through copper, there's going to be some heating associated with that. Historically, in a lot of thermal design processes, this effect hasn't been included, but it's becoming more and more important. One way to capture this in a thermal design is to explicitly model the copper, which you could do probably in a situation like this where there's not that much copper in the board, and apply the current sources and voltage sinks and any kind of electrical resistances and explicitly model that heating effect into the printed circuit board. Here we're showing the results of the analysis where we're getting the temperature prediction of the PCB due to the current flowing through the copper traces and also the current density through the traces. So this is a CFD plus joule heating type calculation. So this is one way to do it, but really not a scalable approach to including this board self-heating. Another modeling requirement for printed circuit boards is the ability to provide temperatures for a thermomechanical analysis, and this is most typically done by the CFD tool being able to export temperatures in a way that the mechanical structural tool can import and map those onto its mesh for the finite element analysis. Next, I'd like to review the various methods to build the thermal model of the PCB depending on where you are in the design process. This table outlines the common modeling approaches for printed circuit boards, but also discusses a couple methods that are unique to Simpson Flowtherm XT and FlowFD. And on the left-hand side, modeling level column, you see we go from level 1 to 4 and the different modeling approaches. And on the right-hand side, kind of the information that you have available or the information that you would import into the tool. Typically in the design process, you start off with a compact thermal model, which means you're just assuming some amount of copper in that printed circuit board by volume. So let's say 20% copper, and then you calculate the effective conductivities, both in plane and through plane conductivities of the printed circuit board, and that's good for some early architectural decisions for thermal design. You're not going to accurately predict junction temperatures of components with that modeling level, but it's certainly useful early in the design process to model PCBs that way. Once the board has been routed, or at least the stack up, and you have an idea of what the layers of each board are going to be, you can progress to level 2, which is commonly known as detailed, or we've started to refer to that level as a layered approach. So you're still on each layer making an approximation for the effective properties of that entire layer, but you are modeling the structure. And this can greatly improve your accuracy for temperature prediction because you much more accurately predict the heat spreading in that top layer of the board where the components are sitting. So between level 1 and level 2, you can generally get quite a bit more accuracy. The next two levels are really unique to our products, or at least the workflow is. Level 3 is material map, and I'm going to spend some more time talking about that in more detail, but it's actually taking the EDA import information, and rather than modeling the copper geometry physically, it represents that entire board as a network assembly with user controls on how fine you want to resolve that copper in that layer. Again, I'll talk about that more in a little bit. Level 4, that's explicit copper, and we've been able to do that for a while. It's a seamless process. Once you've got the routed board read into the EDA bridge, you can choose to model copper either with explicit net. So all the nets are interpreted in our EDA bridge, so you can select a net, and then once you've transferred it over, you can apply the current and voltages like you saw on the previous slides. A newer approach to capturing explicit copper in the thermal model is something we call thermal territory. So you have a critical IC component or a number of critical IC components on your board, and you want to capture that heat transfer path as accurate as you can. So you define a region around that component, both in the kind of lateral directions and through the depth of the board, that you want to model that copper explicitly. So that's what it'll do. It'll model that copper explicitly within that territory, and then outside that territory, it will take a detailed or layered approach. So those are the kind of 4 methods. They're all used depending on where you are in the design process and how critical an IC component temperature prediction is. Now let's take a little bit closer look into the material map. Like I mentioned, the material map represents the printed circuit board as a network assembly or RC network. So a resistor and capacitor network, rather than modeling the actual material properties with the CFD mesh. So it's solved with an embedded network solver. The process would be to subdivide the PCB in a number of patches. So you could think of a black and white image. If you were to pixelate that, how you would get some pixels or some blocks or patches that are white, some are black, and many that are different shades of gray. And that's essentially kind of what this process does, is to kind of pixelate the image of the copper to the resolution specified. There's 2 basic approaches or controls to implement this. The first is what we call fine resolution, where you're capturing the copper with a minimum of 2 nodes of that network assembly across the smallest trace. So you're very accurately representing the material properties in that printed circuit board, and there's really no material approximations. If you use the averaging approach rather than fine, then you do start to see that pixelating approach where there are it looks at the materials present in that patch and calculates an effective conductivity. But again, rather than modeling the physical geometry, it's a network assembly, which you benefit from not having to mesh that, so it lowers the overall CFD mesh count and any kind of complications on resolving that geometry explicitly. So it can save a lot of time in the kind of preparation process, but also the solution process, but also still gives you the control to model it with either a fine resolution or perhaps earlier in the design process where you don't have, say, explicit components on the board, detailed components on the board, and you should use a averaging approach to get quicker simulation times, so you have that flexibility. And finally, this technology is the what provides the ability for the co-simulation with Hyperlinks PI and for this mechanical analysis that we're going to discuss in the upcoming sections. First, we'll talk about power integrity or electrothermal and CFD co-simulation. Before we look at the co-simulation process, I thought it was important to review the actual DC drop analysis. So the power integrity simulation is also commonly known as DC drop or voltage drop analysis. So in addition to the voltage drop, one of the main outputs is current density. In areas of high current density leads to temperature rise, sometimes drastic enough to cause a part malfunction or fires, some severe defects. So predicting temperature rise in these areas depends on how this hotspot is connected to areas of other copper on the board, the surrounding metal in the board, and the board environment. So being able to simulate this in a CFD model that's trying to capture the actual physical environment this board is operating in is going to give you much better DC drop predictions. And like we were discussing, high current densities or this current in the board is another source of heat that is typically not considered. But it is becoming more and more important to consider this during the thermal design and electrical design process. So co-simulation between Hyperlinks PI or power integrity and SimCenter FlowTherm XT or FlowFD determine the amount of heat accurately, because it models the environment accurately, but also includes the heating of the components that are sitting on the board. And from the electrical design, it's important to know that the electrical conductivity of copper varies about 4% for every 10 degrees C. So that results in about 32% over a range of 80 degrees. So this change in conductivity affects voltage drop and current density. So these two analyses really do depend on each other for accuracy, and it makes a lot of sense to use co-simulation to benefit both the thermal design and the electrical design. Before we look at the co-simulation in depth, let's take a look at an overview. The process would start with a file being generated that's based on the routed board, and that file, that common file that could be used, could be ODB++ or IPC 2581B. That board would be read into Hyperlinks PI, and the current voltages would be set up and that project saved. On the XT side, and the process would be the same with SimCenter FlowFD, but we'll illustrate with SimCenter FlowTherm XT. We would read that ODB++ or IPC 2581B into the EDA bridge, process it, filter components, add component powers, swap in component models, all that normal stuff you would do in an EDA bridge. But upon transfer to XT, you would specify that you want to model the actual PCB as a material map. And then once that's in, you can link it up to the Hyperlinks PI project and start the simulation. What happens during the simulation is the DC drop simulation is performed, and then XT will import the calculated powers, at which point XT will run an iteration, export its temperatures to Hyperlinks PI, run the Hyperlinks PI solver, which will calculate the powers, and then XT will re-import those. And that loop will continue until the XT solver has converged or until the solver is stopped. Next, let's take a look at how you would set this analysis up in SimCenter FlowTherm XT and some of the user options you have. On the image to the left that's kind of buried, we see the PCB in the geometry tree. That's after it's been imported from the EDA bridge. If we open the property sheet, and that's the main image we see in front, we see some of the options there. We can see the modeling level is material map. We have an opportunity to change the conductor material, the dielectric material, and also the via fill material. And these are all going to affect the material map calculations. It shows the PCB source was EDA bridge, and then you have the resolution, how much you want to resolve that material map, either fine or averaging. So like I said, if you use fine, you get two nodes across the smallest trace. Also, for via fill material, you can choose void if there is no fill material present. Further down the property sheet, we see an area where we can import sources. So actually, rather than doing a co-simulation, Hyperlinks PI can export a power map. So it can export a file that SimCenter Flowtherm, FlowthermXT, and FlowFD can read into its EDA definition and apply the power in the right areas on the right layer of the PCB. So this is one way to do it if you're not wanting to do a co-simulation. I mean, a co-simulation does require Hyperlinks PI to be installed on a machine. The actual analysis time for Hyperlinks PI is a few seconds, maybe 10 seconds to actually perform that analysis. Again, it depends on the size of the board and the traces you're simulating, but it's very quick analysis. So if you don't have Hyperlinks PI, you could always use a power map file to apply the powers and then improve your temperature prediction by including that kind of self-heating of the printed circuit board. Further down the property sheet, if you're not importing sources, you can specify to do a hyperlinks co-simulation. At this point, you link to the hyperlinks project, just find it on the file system, and then identify which nets that you want to include in this analysis. So the more nets you include, the longer the simulation time, probably on Hyperlinks PI side. So it allows you to just select the nets that are going to generate power in the areas that you're interested in studying in more detail, or the nets that generate the most power. Lastly on this, we'll take a quick look at post-processing the results for the material map. Because it's not based on the CFD mesh, we access results via the property sheet, choose which layer we want to view results on, and then it will generate that layer information. So in this case, we're looking at that layer and the temperatures, and we can choose to look at material properties or temperatures, and we can clearly see how that net is being resolved and the power generated on that net. So that's just a brief look at how you process this model that isn't based on CFD results, but based on the embedded network solver that the co-simulation uses. The last topic I'd like to discuss is the thermomechanical stress, or more generally, just structural analysis with the smart PCB. First, let's discuss the smart PCB. So the smart PCB is a material map that's functionality has been extended. We've looked at how the material map can be used for thermal analysis, conduction in any kind of environment, how it can be coupled with hyperlinks DC drop simulation. But the smart PCB extends it to structural analysis, either thermomechanical stress, like coupled with the CFD, or standalone, just a structural analysis based on this smart PCB that's using that material map definition, that kind of nodal network topology. So it uses that nodal network topology to define its mesh, and that's unique technology recently introduced that I'd like to spend a little bit of time talking about how that could benefit the thermal designer. The material map allows a really robust and easy method to mesh the PCB in FlowFD. So it's not only easy, but it's very accurate because it's really based on that kind of nodal representation of the fine detail. And just a little bit more in depth, the mesh is two-dimensional triangles which are extruded in the third dimension, commonly known as a triangular prism cell. And this procedure is performed on each layer independently of the board. And then, as we know, the copper within each layer is significantly different. So each layer is meshed independently and then glued together automatically using a glue contact between each layer. So all this is a kind of an automated process to quickly and easily set up a very robust finite element model of a explicitly detailed PCB. There are some benefits to this technology and implementation that I'd like to briefly discuss. One is that the meshing approach in SimCenter Flow FD for the structural analysis is automatic, and it's a hex dominant mesh. So generally speaking, I think hex mesh gives you the most accuracy for the least amount of mesh. So generally is a preferred meshing format compared to other topologies. So this is uses this automatic hex dominant mesh, except for the smart PCB, which we looked at uses the triangular prism approach. FlowFD also uses auto glue contact, so there's very little kind of setup time between setting up materials or areas that have different mesh. These are automatically glued together. We already saw the benefit or discussed briefly the benefit of it being CFD and thermo-mechanical all in one tool. So the way this process would work in SimCenter Flow FD, if you wanted to do your typical CFD thermal analysis system design and also the structural thermomechanical stress, you just specify that you want that analysis done after the CFD simulation has been completed. Then it automatically does the thermomechanical stress all in one environment. Lastly, let's the smart PCB finite element method. It's a unique technology based on this material map nodal network to define the mesh, where you don't have to resolve the copper explicitly, but the material map itself is defining where to place the nodes, because it's doing that for the thermal side as well. So it can leverage that definition to create a very robust finite element mesh using the triangular prisms. Next, I thought it might be useful to look at some statistics on the finite element solution offered by SimCenter Flow FD. We have a couple examples here, and it illustrates that the finite element solver is much faster than the mesher. So the solver supports a direct solve method or iterative, but so that's with the direct solve, the solving ends up being quicker than the meshing time. But this also points out that if you're going to analyze models that had different load conditions, you can clone that project within SimCenter Flow FD, and so you only have to do the meshing process once and then the solving process for each cloned project. It also points out that there isn't strictly a thermal analysis required. This can be used for some purely structural calculations in SimCenter Flow FD. Since this is new technology in SimCenter Flow FD, I thought it would be useful to also look at what is currently supported and what is not supported. So currently, a linear solve only. So that assumes that the displacement is assumed to be small, and dependency on the properties on temperature is not strong. Also stationary only, glue contact only. Other types of contact are not supported yet. Modal frequency analysis of the non-load model only. So it does modal frequency analysis, but only if the model is unloaded. Not supported, nonlinear, transient, other types of contact that you see listed there, a preloaded condition, and like I just mentioned, modal analysis of loaded board. What should be known also is that these models that are set up can be set up to be exported to SimCenter 3D for kind of all the analysis that aren't supported in SimCenter Flow FD. And that workflow exists for everything other than the smart PCB. So for other analysis that are using this kind of hex dominant mesh, anything that's not the smart PCB, that SimCenter 3D model can be exported, and all the loads and boundary conditions already applied and ready to run for those other types of analyses that aren't currently yet supported in SimCenter FlowFD. So those are all the major topics I wanted to discuss. So to summarize, we discussed PCB models for electronics thermal design requirements, and their need to support varying levels of fidelity. I introduced you to the material map, which is an innovative method suitable for multiple purposes. It's not based on the CFD mesh, so you can include a lot of fidelity, high accuracy in terms of how you represent the copper in the board without paying a huge penalty in processing, meshing, or solving time. I also pointed out that PCB self-heating is becoming an important consideration for many thermal designs. I quickly looked at how you could set up a Joule heating simulation in SimCenter FlowTherm XT, but that's not really a scalable approach for a lot of thermal designs that have complex nets, many current sources and voltages that you would have to apply. Those are better applied in a power integrity tool. And to get that benefit of that prediction, that Joule heating or board heating, in our thermal design process, it's best done either through reading in that power map, which we looked at, or even better, the co-simulation is going to give you the most accuracy, and it's a very seamless process to include the powers directly from a Hyperlinks PI simulation, and both sides of the design process, electrical and thermal, benefit from that coupling because we saw, the copper electrical conductivity is a function of temperature, and getting those temperatures right for the DC drop calculation is important, and it's only going to be right if we're simulating it in our kind of system level thermal design model. We looked briefly at thermo-mechanical analysis in a CFD environment, and I believe it accelerates and streamlines the thermal to structural workflow in SimCenter FlowFD. For some of that analysis, it can be performed directly in FlowFD, and then much of it can be saved in a format directly read into SimCenter 3D. And the Smart PCB with the material map technology enables design insight based on greater PCB modeling fidelity in less time. So that modeling approach allows you to build a very detailed thermal model, but the finite element model generated from that in FlowFD using that same nodal topology greatly speeds up the mesh generation time and allows you to model that PCB in a lot of detail very quickly. Before I end, I wanted to kind of introduce you to Siemens. You may not be very familiar with Siemens. Maybe you're familiar with Flowmerix from a long time ago, or more recently Mentor Graphics. But I wanted to hit on kind of 5 areas with Siemens. First of all, Siemens itself, as being an engineering powerhouse in its own right, we really have the strength, the vision to continue pushing boundaries, and the financial strength of Siemens clearly allows us to invest heavily in our solutions. Accelerator is our comprehensive integrated portfolio of software, services, and an application development platform. The portfolio accelerates the transformation of business into digital enterprises and unlocks a powerful industrial network effect. Essential requirements to leverage complexity as a competitive advantage, no matter the industry or company. We have an extensive portfolio. The scope of solutions we have for performance engineering support all phases and performance areas within the product development process. Our unique offering both covering simulation and test, which is increasingly important as you think about a future with digital twins and the need to take into account usage data. And finally, our support and services. We have a dedicated support model, and we also have a strong engineering team that work with you on engineering projects and even conducting joint research. Lastly, I wanted to discuss more specifically SimCenter and its test and simulation portfolio and the areas it covers with thermal structural integrity, acoustics, electromagnetics, high and low frequency, and contaminants. The SimCenter portfolio is able to cater to a very wide range of workflow choices, preferences in handling ECAD and MCAD complexity, and different engineering user demographics. With CAD-centric, CAD-embedded, and multi-physics and analyst approaches among the Simpson portfolio, you can achieve faster time to market and with confidence in accurate results. This concludes the presentation, so I want to thank you and hand it back over to the host.